All right, welcome back. So in the first two exercises, you learn how to use two tools like the P4 and time shell and the GNMI CLI to operate with a Stratum software bridge called Stratum BMV2. Now, one of the goals of SDN is to move away from CLIs to manage networks and automate as much as possible. So in the next session, I'm going to talk about ONOS, which is a controller platform that today supports protocols like P4 and time and GNMI. So what is ONOS? ONOS stands for Open Network Operating System. It provides the control plane for a software-defined network, meaning that it acts as a logically centralized remote controller, providing high-level APIs to applications to make it easy for application to control the network. It runs as a distributed system across many servers, and we do this for scalability, high availability, and performance. And ONOS, the focus of ONOS is really for service providers' networks for access and edge applications. Today, ONOS is in production at scale with a major US telecom provider using OpenFlow-based device. There should be an announcement, official announcement this week, and there will be also demos during the event on this type of use case. The first release, ONOS was first released in 2014. The first release to support P4 and time is the Loon release in August 2017. This was a bit after the start of the P4 and time specification work. And the last release we're using today, which is Raven 2.2, it has enhanced support for P4 and time as well as support for GNMI and GNY. This is what we're using today in the exercise, so ONOS 2.2. This is a diagram of the ONOS architecture. On top, we have applications that in the pure SDN style want to control the network from a logically centralized point of view. And to do this, these applications use northbound APIs exposed by ONOS. This northbound API offers service, for example, to get the current topology, to program the network using, for example, flow rules, to receive packet ins, to send packet outs, etc. And this API, ONOS is written in Java, something I didn't mention. So the first place where to look at this API is to look at the corresponding Java interfaces defined by ONOS. But we also provide a way to access this API through REST, either CLI, and in some parts also using gRPC. At the very bottom, we have what we call shared protocol libraries. And this is at the southbound what we use to talk with network devices. ONOS supports different protocols. It was initially designed to work with OpenFlow, so clearly there is support for OpenFlow. But today we also have support for P4 and time, GNMI, and other protocols such as NetConf, for example. In the middle, we have device drivers that allow for device-specific variation of standard protocols. Each device from devices from different vendors, for example, might need to support different way of pushing a P4 and time pipeline. Or you might not be surprised to learn that a simple OpenFlow hello message might be supported differently from different devices. This is where we implement these differences and abstract this away from the application. In the middle, we have the distributed core that maintains the distributed state and provides high availability and scale out. I will not focus on the distributed nature of ONOS, but I'd rather focus on the API and the driver mechanism. So I want to talk about the network programming API. We have three APIs, the flow rule API, the flow objective API, and the intent API. Actually, what we care about in this tutorial are the first two, the flow rule and the flow objective API. So let's take a look. So assuming you want to implement an app to program the network to forward packets from point A to point B, you can do this in two ways. The first way is to write an app that uses the ONOS flow rule API to install flow rules in the network devices. Flow rule is the same flow rule that was the same flow rule concept that was introduced by OpenFlow. So the idea is that you have a match action table, and you can provide entries to this table. These entries are called flow rule using the ONOS terminology. A flow rule in ONOS is then mapped to the corresponding protocol-specific construct if the device uses OpenFlow, if the device uses P4N or other protocols. We have cases in which we use netconf to configure things like optical cross-connects that are abstract with flow rules on the northbound. But using flow rule from an application perspective assumes that the application has knowledge of the pipeline, has knowledge of which table can actually match on, let's say, the Ethernet address, which table can match on the IPv6 routing address or the SEL table. For this reason, we provide another abstraction that is called flow objective. Flow objective is a pipeline agnostic forwarding abstraction. It actually abstracts a simplified logical three-stage pipeline. I'll talk about this in the next session. The idea is that applications can program the network in a way that is almost independent of the device-specific pipeline. And flow objectives can then be mapped to multiple flow rules by driver. So for example, we have a driver for the OFDPA pipeline. If you're not familiar with it, OFDPA is a OpenFlow switch agent provided by Broadcom for Broadcom Silicon that abstracts a very specific pipeline in terms of which tables are available, which actions can be performed, and how these tables are arranged in the pipeline. We can map flow objective to a single table pipeline. This was the abstraction of the first version of OpenFlow, but we can also map flow objective into a P4 program-defined pipeline. Just to give you an example, assuming we want to implement a peering router that inserts, that wants to program our devices using forwarding entries that match on the switch port, the MAC address, the VLAN, and the IP address. If we have devices from different vendors, here we make the example of OpenFlow 1.3, and because that's why the Flow Objective API was introduced, because with OpenFlow 1.3, we started to see differences in how vendors implemented the protocol, and we started to see differences in the pipelines. So if we take a device supporting OpenFlow 1.3 from HP and one from Broadcom supporting OFDPA, you will notice that the same forwarding entry is mapped to different tables in one case and in the other, because the tables are different. But the end result, in terms of forwarding behavior, can be the same. The flow objective service in ONOS, and so the flow objective API, serves to abstract this complexity from the application. So the applications can express their desires in terms of like match-action relationship, and then these match-action relationships are then mapped to the flow rule specific to the pipeline used by a given device. I talked about driver, so I want to clarify what I mean by driver in ONOS. So ONOS defines a set of APIs to interact with devices, and we call this API behaviors. Example of behaviors are the device description discovery, the flow rule programmable, the port statistics discovery, and the pipeliner. These APIs are used by ONOS, for example, to read device information and ports, to write and read flow rules, to get statistics of device ports in terms of port counters, or for example, to map a flow objective to a collection of flow rules. So behaviors are essentially Java interfaces. So these Java interfaces are defined by ONOS, and a driver is a collection of one or more implementations of these interfaces and this behavior. And implementation can use the shared protocol libraries provided by ONOS. So the idea is that you can have a driver that uses, for example, both the P4N and GNMI protocol libraries. You can have one driver that uses only P4N or netconf, and etc. So before we move on, let's derive a few key takeaways from these few slides I just presented. So when using ONOS, it's important to keep in mind that applications can be written in a way that is independent from the switch control protocols. And that's because ONOS offers high-level network programming APIs. So the same app can, in principle, work with OpenFlow and P4N devices. We offer mainly two different types of APIs to program the network, the flow rule API and the flow objective API. The flow rule API is pipeline dependent. The application needs to be aware of the specific tables in the pipeline, the flow objective API is pipeline independent. Just to make an example, when you instantiate a flow rule, you have to pass a table ID. When you instantiate a flow objective, no need to pass a table ID. Table IDs will be derived then by the driver, which is responsible for translating flow objectives to many flow rules. The flow objective API was implemented to enable application portability. And you can see some overlap with the goals of P4 for fixed function switches. The reason the flow objective API is there is because it was created as a consequence of the pipeline heterogeneity that came out with OpenFlow 1.3. And as I said before, there's definitely some overlap between the two, flow objective and P4 intention. So the idea is that an app using flow objectives can work with switches with different pipelines. For example, switches with different P4 programs. And I'll give you examples of that in a second. So now let's talk about how ONOS support data plane programmability using P4 and P4 runtime. And it's important to talk about this because ONOS was initially designed to work with fixed function switches, mainly using OpenFlow. So the ONOS core abstractions, even if they are independent from the protocol specifics, they are definitely inspired by OpenFlow. So if you look at the ONOS APIs, you will find a reference to the same header supported by the OpenFlow protocol. You will find a reference to the same actions that are defined in OpenFlow. So when we start working on adding support for P4 and P4 runtime, we set a few goals, a few design goals that are the following. So we wanted to allow ONOS users to bring their own P4 program. We don't want to restrict applications to just a small set of P4 programs that are predefined in ONOS. And an example is today's tutorial. You are using a completely arbitrary P4 program that implements a IPv6 router, but it could do something else. It could could serve as a prototype for IPv8, for example. We want ONOS to be able to allow control of that P4 program. ONOS today comes with a good set of built-in applications that provide services like topology discovery, host discovery, proxy ARP, integration with external routers like BGP speakers, and et cetera. And we want to be able to reuse the same built-in applications with potentially any P4 pipeline without changing the application itself. And today you will see this because you'll be asked to make few changes in ONOS to be able to use the packet in, packet out mechanism offered by the P4 programs to enable simple services like topology discovery and host discovery. So you don't have to write this, the services by yourself, but you can reuse what's built in ONOS today. At the same time, we want to allow new applications to control custom new protocols as defined in the P4 program. So again, if you're thinking of prototyping IPv8 or 10, using P4, and you also want to prototype the control plane, you should be able to use the same ONOS API to essentially specify forwarding entries using whatever match fields and actions you have defined in your P4 program. So how do you do that in ONOS? The key to everything is what we call the Pipeconf, which is a new API in ONOS, where Pipeconf stands for pipeline configuration, and that's what allows you to bring your own pipeline in ONOS. So the idea is that we can package together everything that is necessary to ONOS to understand, control, and deploy a given pipeline to a device. A Pipeconf can be provided to ONOS as an application binary, so we can use the same .oar format, which stands for ONOS archive. It's like a jar file, essentially, with jar archive with some files inside, and it contains mainly three things. So a Pipeconf contains a pipeline model, which is a description of the pipeline understood by ONOS, and this is automatically derived from the P4 info file that is generated by the P4 compiler. So in terms of which tables are available, which match fields, which actions, what's the packet in, packet out metadata, this information is all contained in the pipeline model. It contains also target-specific extensions to deploy this pipeline to a specific device. So for example, if you want your Pipeconf to be able to program the BMV2 software switch, then you have to include the BMV2 JSON along with the P4 info file. If you want to be able to program Tofino or an FPGA-based device, then you have to include as well the Tofino binary or the FPGA bit stream that is obtained from the P4 to FPGA compiler. Finally, the Pipeconf includes what we call pipeline-specific driver behaviors, meaning that the Pipeconf can include an implementation of those driver behaviors that depends on the pipeline. And an example of that is the pipeliner driver behavior used to map flow objectives to flow rules. So Pipeconf contains an implementation of this mapping that is specific to the P4 program or pipeline model. So when you put everything together in the ONOS architecture, that's what it looks like. So you have Pipeconf that can be made available to ONOS using a Pipeconf store. And at the bottom, you have your Stratum devices supporting APIs like P4 Runtime, GNMI, and GNOI. And on top, we can have two different types of application. We can have pipeline-aware application and pipeline-agnostic application. By pipeline-aware application, again, we mean applications that are aware of the specific pipeline. And this application can program the network using APIs like flow rule, specifying, for example, match fields and actions using the same names as in the P4 program. So if you created a table that matches on header.myProtocol.myField, then you should be able to use the same string name in the ONOS application implementation, providing flow rule for that. Then we have built-in applications that program the network using flow objectives, and these flow objectives are translated to the flow rule specific to the pipeline by a number of translation services that are part of the ONOS core. Today, we have different Stratum-based devices in ONOS to control different Stratum-enabled devices. We have Stratum BMV2, Stratum Tofino, and what's missing here is Stratum FPM. I should make sure to update the slide. Stratum FPM is essentially the Stratum target for fixed function switches like those based on Broadcom Tomahawk. So today, we have 3 Stratum-based drivers. So once you have your Pipeconf and once you have a Stratum-enabled device, how do you connect that to ONOS? How does it work? So as a first thing, you have to register your once ONOS is running, you have to register your Pipeconf with the system, meaning that you have to provide Pipeconf and an ID. So this Pipeconf will be identified by ONOS with a unique ID. Second, you push to ONOS a JSON file that is called the network configuration that provides for a given device identified by an arbitrary ID, a management address in terms of the gRPC server endpoints, so IP address and port, and a Pipeconf ID, as well as the driver to use. What ONOS will do after that is use the driver to start a connection to the device. We call this the handshake. In the case of Stratum, it will open a connection to the gRPC server running on the switch. And it will then deploy the Pipeconf using the target-specific extensions like the BMV2 JSON and P4 info using P4 runtime. In this case, we use the set pipeline config RPC, which is defined in the P4 runtime API. Once we have deployed a Pipeconf to a device, then we can write applications that can program this device using forwarding entries. Again, we can use the flow objective API or the flow rule API. In the case of pipeline agnostic API providing flow objectives, what happens then inside ONOS is what we call a 3-phase translation. So how do we go from a flow objective to a P4 runtime message that describes a set of table entries that are equivalent to that flow objective? So first of all, we map from flow objective to many flow rules. And this is done by this blue box called the pipeliner, which belongs to the Pipeconf driver. As you can see, the legend here, we have the blue boxes are essentially part of the Pipeconf. The green ones are the driver, protocol driver, so everything that is specific to P4 runtime in this case. And the red boxes are ONOS core components. So flow objectives are mapped to many flow rules by the Pipeconf provided pipeliner. Then each flow rule is mapped to a table entry, which is an internal representation that we use to map, for example, ONOS known header fields, like the Ethernet destination, to the corresponding name of the same header field in the P4 program. And this is achieved by using another Pipeconf provided behavior called the interpreter. And I'll describe this in a second. After we have the table entry, then the table entries are translated to P4 runtime protobuf messages by the P4 runtime client. So this is where we map, for example, P4 names to their numeric identifiers as found in the P4 info message. In the case of pipeline-aware applications using the Flow API, clearly what we're skipping is one, the first translation from flow objective to flow rules, but then the steps are the same. And again, in this case, you can use the same name for match fields and actions as found in the P4 program. So I mentioned this pipeline interpreter, which is a driver behavior that can be provided as part of your Pipeconf. And the goal of this interpreter is that of providing a mapping between ONOS well-known types and P4 program-specific ones. So for example, assuming you want to install a flow rule that matches on the Ethernet destination address, you can use enum that is defined in ONOS to identify the Ethernet destination address, but then the mapping to the actual name in the P4 program, or better, in the P4 info file, this has to be provided by someone. So this mapping between this enum and this string name is provided by the interpreter. Same thing for packetins. So in ONOS, we have applications. When ONOS receives a packetin, again, a packetin is a packet that is intercepted by the data plane, and it's sent to the control plane for further inspection. Applications, what they receive is essentially an instance of a Java class called inbound packet, and they can access, for example, the original ingress port where this packet was received by using this method chain. So received from port. How do we map the port value to the metadata field contained in the packetin message? If you remember from the P4 program you saw in the first exercise, you can specify which metadata field you want to associate with your packetins, and you can give them arbitrary name. In our P4 program, for every packetin, we carry metadata called ingress port, like name ingress underscore port. The interpreter is where we provide a mapping essentially between the inbound packet members, identifying the port, and the P4 info specific ones. Same thing for packet outs and other entities. So this mapping is provided by the same P4 program writer. So the idea is that if you want to use P4 to program network devices, and if you want to use ONOS as the control plane, and if, actually, there should be a slide after this, but I can answer this question now. The idea is that if you want to use built-in applications that use ONOS known types, like the Ethernet destination enum for the match fields, then you have to provide a map. You have to tell ONOS, what's the mapping between this header field and the actual P4 program specific names. And this is usually done by the same person or team that writes the P4 program. So you will have to write P4 code and Java code, package them together, and give it to ONOS. We'll compile the Java classes and then give it to ONOS. ONOS 2.2 supports a number of features that are P4 runtime specific. Today we can manage table entries, P4 runtime table entries using different APIs like flow rules and flow objective. We can handle packet in, packet out using an high-level northbound API called packet service. We can deal with things like action profile groups, members, multicast groups, and clone sessions using the northbound API, ONOS northbound API called group service, and etc. There are still some unsupported features of P4 runtime, like parser value sets, registers, digests, and we're looking for some community help needed if you're thinking of contributing to ONOS. This could be a good way to start. So before we move on to the next exercise, let's do a quick recap of the workflow to use ONOS and P4 together. So if you want to do that, the first thing you have to do is write a P4 program and compile it using your P4 compiler. obtain the P4 info file and the target specific binaries. In the case of BMV2, this will be the BMV2 JSON file. Then you can package together this P4 info file, BMV2 JSON, or whatever target specific binary, along with some Java classes, Java implementations, like the pipeliner, if you want to be able to use built-in applications that program the network using flow objectives. So you have to tell ONOS how to map flow objectives into your specific pipeline. You can decide to provide an interpreter, do the same thing and map ONOS known header types actions to P4 program once. And you can provide essentially any driver behaviors that depends on the pipeline as part of the Pipeconf. Once you do this, you can use existing built-in pipeline agnostic applications, and these are applications that program the network using the flow objective API, or you can decide to write new pipeline-aware applications, which are applications that are designed with knowledge of your P4 pipeline in mind. Is there any question before we move on to the exercise overview? Is everything clear? Hopefully we'll be more clear with the exercises. Okay, so the goal of the third exercise is to start ONOS with a set of built-in applications and a custom application as well as a Pipeconf, and use that to control our 2x2 fabric. So at the very bottom, we have Mininet running inside a Docker container. This is the same Mininet container you started in exercise 1 and 2, with 4 Stratum BMV2 instances in a number of IPv6 hosts emulated using Linux network namespaces. Then we have another Docker container, which runs ONOS 2.2 in this case. We start ONOS with 2 built-in applications called the LLDP Provider and the host provider that are used for things like link discovery and host discovery. Then the tutorial repository contains code for a Pipeconf implementation that is based on the P4 program you saw in exercise 1. And we also provide an application implementation for the same P4 program. This tutorial app is essentially the control plane or your IPv6 fabric, or at least the fabric you're trying to build. The difference between the built-in apps and the tutorial app is that the tutorial app is a pipeline-aware application, so we program the network using the same table names and actions names as the P4 program, while the other 2 use the flow objective API. Finally, we have a netcfg.json file, which stands for network configuration, that specifies the IP address, gRPC port, the Pipeconf ID driver and everything else of the Stratum BMV2 switches we're trying to control. So the exercise steps are the following. You will be asked to modify the Pipeconf Java implementation. Don't worry, it's like 2-line changes. It's very simple. And also, please remember, there's a solution directory. So if you feel stuck, don't hesitate at, looking at the solution. The idea is to modify the Pipeconf Java implementation to map the P4 runtime packet in, packet out messages to the internal ONOS representation of that. And we need this feature, packet in, packet out, because we want to be able to do link discovery and host discovery. And I'll explain how that works in a second. So after modifying the Pipeconf Java implementation, you're going to start ONOS and Mininet. You're going to load the application you just modified along with the Pipeconf and the netcfg.json file. ONOS will discover the Stratum devices, and the built-in apps will try to first discover all links. And again, this requires packet in, packet out to work. And then we'll be asked to verify ping for us in the same subnet. Essentially, you'll be using the bridging part of your P4 program. So how does topology discovery works in ONOS? We use a mechanism that is based on LLDP packets. So the idea is that ONOS is connected to multiple switches using P4 runtime. And for every switch, what ONOS does, it sends packet outs out of the old switch ports. So switch ports are discovered using GNMI. So if there are, for example, 10 ports, ONOS will periodically try to send 10 LLDP packets out of the different 10 ports. Each packet is tagged with an identifier of the origin switch and port number. These packets are received at the other end, and they are intercepted using packet in. So they're sent back to ONOS, which now is able to correlate the information contained in the packet in to discover the link. So in this case, ONOS is able to learn about a link by looking at the LLDP payload, in which we contain that contains a reference to the original switch and port number where the packet was originated, and also by looking at the packet in metadata. So from which switch port this packet in was received. That's how we're able to discover a link. And this is made available by an application called the LLDP Provider application, which what it does, it listens for device events. So every time a new switch connects to ONOS, or actually I should say every time ONOS connects to a switch, and that's because in the P4 time paradigm, ONOS is the client and the switch is the server. So every time ONOS connects to the switch, a device event is generated, and this application picks up the event and starts sending LLDP packets out of the switch ports. At the same time, we install a flow objective that matches on the ether type. So we want to be able to match on LLDP and VDDP packets and send that packet to the controller. So that's how we generate the packet in. Then we have an host provider applications that provide host discovery capability. So to implement bridging, we need to implement behavior that is similar to MAC learning. So the idea is that we should be able to learn about hosts in the network to be able to populate the bridging and the routing tables. So what ONOS does, it installs a flow objective that matches on packets like HARP, NDP, DHCP request. All these packets are cloned to the CPU, so the controller. And based on the information contained in these packets, like the MAC address, the IP address of a given host, along with the switch and the ingress port where the packet was received, that's how ONOS is able to discover new hosts in the network. The Pipeconf we use today has this ID, ONOS project NGSDN tutorial. It provides an implementation of this driver behavior. So we have a pipeliner implementation, use to map flow objectives that are needed for the LLDP and the host provider apps. So it's a very simple pipeliner implementation that maps flow objective to the ACL table. You can look at implementation if you want, but it's not necessary. And we use a P4 runtime feature called clone sessions to be able to clone these packets to ONOS as packet ins. Then we have an interpreter implementation that it's used to map the packet in, packet out metadata to and from the ONOS internal representation, and to map the ONOS known headers to P4 info specific ones. This netcfg JSON file that I described before, it's a simple JSON file that contains for each device, again, the gRPC endpoints, the driver to use, and the pipeconf. Here, the host part of the management address, it's simply as minute, and that's because we're running this minute container using Docker Compose, so ONOS is able to refer to whatever ports is made available in minute by simply using the minute hosting. But if you're trying to control a real device, a real hardware device, that's here you need to provide either an IP address or a host name that is reachable by the controller. This is the architecture of the custom application that is provided to you along with the Pipeconf. We have mainly 3 components. By component, I mean an OSGI component. It's a runtime entity that it's activated as soon as you activate the app. You can see the app as comprising different entities, each one taking care of different functionalities of the pipeline. So we have a component that takes care of populating the bridging table based on host learn. We have a component that populates the routing table based on host knowledge and interface configuration. This will be the focus of the fourth exercise. And finally, we have the Pipeconf that is registered at simply at app activation. I just want to, how many slides do I have? Okay. At the end of this, the second part of the exercise, after you're able to connect ONOS and discover the topology, you'll be asked to ping host in the same subnet. And so you essentially will be using an implementation of bridging control plane that is provided to you. So I just want to explain how the bridging component that I showed before in this slide, how it works. So how do we implement bridging in an IPv6 network? Remember, this is IPv6, this is not IPv4, so we have slightly different protocols. The main difference is that we're not using ARP, but we're using NDP, which stands for Neighbor Discovering Protocol. The packet format is different, the purpose is pretty much the same. So what happens when a host tries to ping another host in the same subnet? The first host will send a so-called NDP neighbor solicitation request. This is equivalent to an ARP request, trying to resolve the MAC address of the other host. We want the switch to be able to replicate all these NDP packets to all the host-facing ports. And that's because at this point, we don't know what's the location of the target host. So we simply broadcast the NDP request to all ports. When the other host receives this NDP request, it can reply with a so-called NDP neighbor advertisement message. And because ONOS is intercepting both NDP NS and NA packets using packet-in, ONOS at this point is aware of the location of two hosts, host A and host B, and which ports they're attached to. And because of this knowledge, and essentially we receive a host event, ONOS takes care of inserting two bridging rule in the bridging table to forward packets in the two direction based on the MAC destination. And since picture is better than 1,000 words, so let's use a diagram for this. So assuming we have ONOS, our lift switch, and three hosts, H1A, 1B, and 1C, that are part of the same subnet. Assuming we want to ping from H1A to H1B, the first thing that H1A does is send an NDP NS message to learn the MAC address of H1B. The switch at this point is already programmed by ONOS to replicate using multicast replication to replicate the NDP NS request out of the other host-facing ports. But we also use a so-called CPU clone session to send this packet to ONOS as a packet-in. So if you went through the P4 program in the first exercise, you should already be able to correlate these different steps to different tables in the pipeline. So we have a table that matches on NDP NS request. We have a table, the ACL table, that allows to clone packets to the CPU. And we have the traffic manager in the middle is responsible of replicating packets. So when ONOS learns the location of H1A, it will insert a Unicast entry to forward packets to H1A. At this point, H1B will reply with an NDP NA message informing H1A of its own MAC address. This packet is also intercepted by ONOS, and that's how ONOS learned the location of H1B. At this point, we have two bridging entries, and Unicast forwarding between the two hosts can happen. This is just a description of the implementation of the bridging component. You can look at it, you can ignore it, and take it for granted. The idea is it's a very simple implementation. We listen for device and topology events, and based on this knowledge, we program the different tables of the pipeline. So in ONOS, we use sometimes exotic terminology when it comes to very simple things like MAC junction tables. During the exercise, you will see terms like criteria, treatment, or PI classes. Criteria is essentially a collection of match fields used in a flow rule. So this is equivalent to the match part of a match action table. And the treatment is equivalent to the actions instructions of a flow rule. We also have this thing called PI classes, like PI table ID, PI match field, PI criterion. You will see this in the exercise. You can think of this as the Java equivalent of P4 runtime entities. And with this, I'm done with the exercise overview. Hopefully it wasn't too much. As before, you can open the instructions either on GitHub on your virtual machine and work on exercise.